Dr. Moore invented Moore's law in 1965, which is almost 50 years ago. And as a young engineer at Fairchild, he boldly predicted that the technology would allow to double the transistor count every year. This was then modified a few years later, I think in 1971 or 72, to his famous prediction, which is now really known as Moore's law, that things would double every other year. And keep in mind, this is not a law about nature like a physics law or chemistry, etc. This is really a prediction about the advances in manufacturing processes that would allow, the combination of manufacturing equipment and underlying process technologies to make these kind of advances. And it has been, I would say, one of the most remarkable predictions in the history of mankind. The most amazing thing about this is that, 40 plus years later, 50 years later, I'm losing track here, 50 years later, it is right on schedule, meaning there was a time period, I would say, a few years ago, like around 2018 and 2019, where Intel Corporation, unfortunately, the people, Moore's law was a founder of Intel, who invented Moore's law, fell behind because they didn't order the latest ASML extreme ultraviolet machinery. And obviously, without the right manufacturing equipment, you cannot stay on track. However, TSMC and others who kept investing in the latest equipment, have been able to be on this curve. It's getting more expensive. The machines are very expensive. The fabs are ultra expensive. But the currently largest single transistor, ignoring people who are building single wafer chips, is around 200 billion transistors. And everybody now believes that by 2030, the logic gates, not memory, flash memory, you can build many stacks, like 128 or more layers of silicon, and have, I don't know how many trillions, but in logic gates, which is a better measure, it will hit 1 trillion transistors by 2030. So this has been, the ultimate in cost reduction, in functionality improvement, in the thing that really became the fountain of youth, if you will, of not just Silicon Valley, but any technology that incorporates, information technology and communication, etc. So Moore's law is well understood. 3 nanometer taping out now, 2 nanometer in 2025, 1.8 nanometer, 1.5 beyond this. But there's another aspect of Moore's law that I think is much less well understood, which is my next slide. Next slide, which is the ultimate economic impact of the semiconductor industry over the years. Back at the time when Moore's law was invented, it was a tiny industry. In fact, I still remember the first Intel advertisements from 1973, where they were trying to figure out what is a microprocessor good for. And they always come up with this example of controlling the red lights at the intersection. So the early applications were really quite, call it, limited. And of course, you only had a 4-bit microprocessor, and then there was 8-bit, and then there was 16-bit, and then there was 32. But overall, the semiconductor industry has grown very similar to Moore's law. This year, it is expected to hit over, the year isn't finished yet, but it's expected to be around $600 billion. And most analysts predict it will be $1 trillion by 2030. I mean, there may be the industry has some pocket holes, the so-called boom and bust cycles. Right now, there's too many memory chips, so memory chips are getting cheaper, and as a result, people will consume more memory chips. But if you look at the long term, it has been an unpredictable growth, and again, well on the way to $1 trillion. But what is even more important is the impact semiconductors have on the economics overall. And this is besides the fact that the number of devices or chips being built is already over 1 trillion, and trillion is your United States trillions here. I don't know how to translate in Germany, I'm sorry. But 1 trillion devices, packaged devices, have been sold this last year, actually, and many trillions will be sold in the future. And certainly transistors on these chips have been the one thing that has been manufactured in higher quantity than anything else in the history of humankind. But the next slide, which is even more important, is the worldwide economy, which is roughly, plus minus 100 trillion. So this is all the countries, all the GDP, if you will, of all the countries combined. Out of the worldwide economy, semiconductors are an input, like an important ingredient to at least 12% or $12 trillion in products. And this includes, cars, washing machines, any kind of manufacturing equipment, anything that involves pretty much anything these days that has any intelligence. Now, it doesn't include like oil and gas and commodities, things like that, or food we eat and so on, right? But of all the modern kind of products we are surrounded with, starting with the smartphone, they have all a lot of chips. So if we didn't have chips today, let's see, another way to say this is at least 10 or 12% of the economy would be missing. And this is also a sign of how important these chips are to the overall market, having led essentially the wealth creation and the innovation over the last many, many years. The internet as we know it, all the software we know it, runs on semiconductors, of course. And one can argue that, excluding biotech and all the advances made in DNA engineering, call it, that semiconductors have been the most important driving force of innovation in the last 50 years, certainly. Next slide. Now, the part of the market, of course, that's most visible to chips is the smartphones. There's billions and billions of smartphones out there, and the servers and the compute in the cloud that are behind this to enable all these incredible applications we see today. And there's millions and millions of servers in the cloud. Next slide. And just to focus on that for 1 second. Next slide. There's some pictures what this looks like. You've seen the pictures. They're football full-size fields of servers, 100 megawatts and more data centers, cycling away day and night to deliver these services, which we're all used to. Next slide. Now, again, looking at the economic impact of this, the world's most valuable companies, which I guess Facebook has fallen a little bit on hard time lately, but certainly 6 months ago, there were Apple, Google, Microsoft, Amazon, and Facebook, adding up to, trillions of dollars of market value. Next slide. They all rely on, semiconductors and software delivered services. And to give you another feeling of the change that's happening, historically, a lot of people built their own data centers, in-house to have their HR, payroll, manufacturing, ERP processes locally. And there's a big shift to shift these things in the cloud. This was a forecast from Gartner from a few years ago, where they thought this year, 2022, there would be about $330 billion in cloud services. It turns out they were very conservative. Next slide. So the current forecast is it's almost $600 billion of cloud services. I'm sorry, almost $500 billion this calendar year, and going to $1 trillion of IT, delivered in the cloud from huge cloud data centers into the products that used to be on the enterprise. So these are not search and social. These are business applications like Salesforce and Oracle and all these applications that used to run more in-house. Next slide. Oops, and this is somehow missing. Next slide. And then this is before we get to artificial intelligence, where the biggest excitement, I would say, that today in computing is, the ability to do these very high density chips that have, 100,000 of arithmetic units and generating, literally exaflops in a fairly small cluster, and they're optimized for AI, that are delivering the most, unexpected, unparalleled improvements in both productivity and ability to build better products or to sell them in a better way or design them in a better way. So we don't want to dwell too much on the AI here, but for sure, that is one of the most important use cases of semiconductors, and more so in the future, is how to, essentially simulate the kind of things we're doing in the human brain, except in a machine a million times faster. And the really great thing about AI and machine learning is it can improve almost anything. So the forecasts of what AI will do for the economy in terms of economic growth are in the trillions of dollars. And it is, again, viewed as one of the big innovation areas. Next slide. So now we get back to something perhaps more relevant or important in Europe, which is how does this all impact the car industry? And I wanted to focus on cars because cars historically have been viewed as fairly low tech, right? You have the internal combustion engine, which is now becoming a motor, electric motor, and batteries. But the other more interesting thing about cars is the amount of chips and transistors going to cars to make them better. So next slide. And let me start with this very popular notion that the car of the future is a smartphone on wheels. In other words, people have recognized that if cars are smarter and they have a better user experience or customer experience, then people will perhaps buy the latest car, just like buy the latest smartphone, because it's more fun to drive that car than an older car. Next slide. And this is a picture, in fact, the only picture that Apple released of their future Apple car operating system, or what maybe a future Apple car may look like. And, it has a lot of displays. The one below it looks like a big smartphone. The other one is like a big screen left to right on the windshield. And they just showed this one picture at a conference, the user conference 6 months ago. Next slide. Will you believe that in a recent survey, the majority of this was a United States service, ranked the future Apple car, which hasn't been built yet and nobody knows what it really looks like, as the car they would love to buy. Next slide. I mean, to me, this was actually shocking. Apple, who never built a car before and has never announced a car, was ranked third highest in the world of a car that people would like to buy. It already has the highest quality impression of any car, even though the car doesn't exist. Remember, they're ahead here of Tesla, Lexus, BMW, Audi, and even Porsche. Now, how is this possible? Next slide. Okay, next slide. Sorry. Well, the real issue here is that people believe, smartphones, which has been such a good experience, will actually improve the car experience. And it is very likely that people will care very much about the software that the car has. Next slide. And, there's of course a lot of software in the car. There's the ECU, the electronic control units that run the engine or the brakes or whatever. They're very important, but nobody sees that and nobody cares about that in terms of software. Then there's all this new AI software that will help with the automatic driving, or certainly with higher safety in driving, and that's very important, but again, nobody sees it. And then there's the software that defines the user experience, which is, how do we interact with the car? And that is something people do care about. So next slide. So the situation here is there is two competitors like usual. There's the Google Android Automotive Initiative, and Google is actually ahead of Apple. They have about a dozen partners in the world, and a lot of cars today actually use the Google software to deliver, some of this functionality. Next slide. And also, it is true that Google worldwide actually has higher market share than iOS from Apple. So in Germany, for example, Google has 57% market share, and the Apple iOS is 40%. But it is also true that it is almost like an end user preference. The people who have Apple smartphones may prefer the Apple car, and the people who have Google phones, they may prefer the Google OS in the car. So car makers may have to support both operating systems. At least that's my outlook at this point. Next slide. And it's hard to predict. Obviously, the Apple software hasn't been shipped yet. The only thing they showed was this beautiful picture, but they are working with a number of OEMs and manufacturers to embed this into the car. Next slide. Next slide. But let me go back to chips here, which is, what does it really take to create this added intelligence in the car and to have something that is in fact a smartphone on wheels? Like, how many more chips do we need in the car? And the answer to that is actually a little more shocking than you may believe. So next slide. So there are people who take the Apple phones apart, right? There's a services that analyze exactly, how many chips are there and who makes the chips and who is winning and who is losing. This is a teardown of the Apple iPhone 13. I don't have one on the latest phone yet, but this is like an X-ray picture. There's 3 major circuit boards. Next slide. And people have analyzed exactly who makes the chip. A lot of them are Apple designed or Apple unique. Some of them come from NXP or Skyworks and Texas Instruments and Qualcomm, of course. Next slide. The big A15 chip is from Apple, in-house designed, but they don't make their own memory chips or flash chips. Some of these come from China. Next slide. So these are 3 circuit boards. Now, next slide. Adding it all up, the iPhone only has 24 chips. I know this is hard to believe, but obviously there's not a lot of room. In fact, what's really amazing about the iPhone is that with a 10-hour battery life, in the average, it only consumes 1 to 2 watts. Now, if you talk all the time, it would be more. But it is actually truly a marvel of engineering how to package this much horsepower functionality, which is essentially the power of a mainframe from 1980, into a device that consumes 1 to 2 watts. And it's certainly an inspiration of what's possible using the latest, Moore's law microprocessor technology. Next slide. Well, how does this compare with the cars? Well, believe it or not, the current average car, I'm not making this up, has 800 chips. And the prediction is that the car by 25 will have 2,400 chips. Like, why does a car need 2,000 chips if the iPhone, or 2,400 chips if the iPhone has 24 chips? This shouldn't be possible, right? And it kind of explains the chip shortage we're seeing in cars. Well, there is a problem here. Next slide. Which is cars, the way they're designed, they have a separate microprocessor control unit or ECU for literally everything. There's one for the brakes, there's one for the seat adjustments, there's one for the infotainment, of course. There's a whole subsystem for networking these things together. It's a weird way to design an IT system, is just like all these distributed functions. And, it is a problem in terms of number of chips. So next slide. And this is, by the way, before we get to LiDAR. So the current number of chips is really driven by the ECUs, the electronic control units, not by LiDAR, which almost no car has today. So the problem here is, I think cars have to be a little re-architected to use more centralized processing and fewer chips, and just having essentially sensors for all these functions. They need to sense, but do the processing in a more centralized fashion to reduce the chip count, not to increase it. And next slide. So there are, in fact, there's one car company in particular that adopted a more centralized architecture, which is Tesla, and they had less problems finding the chips for the cars than other people that use more traditional designs. But what needs to happen here is a rethinking of, I think, both of the supply chain and the design processes around chips for cars, because cars actually have a very large volume overall. And car companies, in particular the large car companies, can justify modifying that chip supply chain. It will require some investment to optimize it for their needs. Next slide. Next slide. So if you look at the car business, the average car today, and this is actually, let's focus on electric cars going forward. There's about $1,000 worth of chips in the car, and this includes in the future the chips for the power conversion, right? Today it's maybe more like $500, but it's definitely going up with the electric cars. And of course, we need the power converters is kind of a separate industry. And this is before we get to LiDAR and more 5G networks in the car. Next slide. And overall in the world, cars, or the auto industry worldwide, is about 10% of the total chip market. So when you remember earlier, we talked about the chip market being $600 billion this year. The car industry is almost 60 billion out of this, which is a large player. In fact, chips are almost as large as, call it the consumer, actually larger, well, comparable to the so-called consumer category, not as big, of course, as communication computers, but it's a very large portion overall. Next slide. And this breaks down, of course, to, and more importantly, it has the highest growth rate of any application. So the demand for chips, believe it or not, is the fastest growing part of the semiconductor industry, right? Next slide. And part of the, it's worldwide, 20% is North America, Europe is 21%, Asia Pacific, over half already. So you can see where the chips are going. Anyway, next slide. And this is a little hard to read, but the top line, you can see actually here's estimated around 50 billion, and then it breaks down between all these different systems in the car that needs chips. Next slide. So here we have, how the chip industry slowed down the car industry for the last 2 years, and people were waiting for the car. Some cars had a year-long lead time or waiting time because they couldn't get the last chip to finish the car. I mean, this should have not happened. Now, part of the reason this happened, next slide, is that cars actually use a lot of chips that are really antiquated. The cars are the biggest consumer of 90 nanometer and 110 nanometer and all the technologies that they barely make anymore. And nobody is investing in 90 nanometer new fabs because sooner or later you don't need them. At least that's the idea. Well, they didn't count on the fact that cars are using more and more of these same old chips, and they couldn't make enough. And then there was a fire in the factory in Japan, which further slowed it down. The bottom line is the chips that are the hardest to get right now are actually the oldest chips, and those are the ones that slowed down the car industry. And maybe one still has to invest in more capacity there. But the bottom line is cars need to advance to use more contemporary chips and ideally use fewer chips, which will help them to actually save cost and to improve reliability. So cars need a fresh design approach, but it is true that in the car business, you have very long design cycles. People are designing new electronics for cars today. I hope that they will ship in 2026 or whatever it takes 4 years to get to production. I think they need to shorten that design cycle and really, own the decision or own the future of how to design a more efficient car. Okay, next slide. Yeah, we talked about this. Next slide. Now, let me switch topics here to the foundry model. And of course, the most foundry and the biggest and the most, at one point, the most valuable chip company in the entire world, TSMC, is really, I would say, an amazing success story. When the company started in 1985, or when they tried to start the company, they actually had trouble raising the funds because there was no foundry business model. Nobody actually believed this would work, believe it or not. Every chip company in 1985 had their own factory, right? This was when people had to invest in the latest factory equipment to build chips. You couldn't start a chip company without a factory. And finally, they got off the ground, and immediately it changed the future of chip companies, where all the new chip companies that started after this were fabless because they didn't have to build a fab, and you need much less money if you don't build a fab and you just design the chips, right? So the other big chip companies that people know today, NVIDIA, Broadcom, even AMD, right? They all use TSMC as the foundry now, or even actually for many, many years. And this allowed them to grow with the latest process technology, to the point where TSMC today makes, is really the only foundry that has the most advanced process in high volume production. Samsung is trying to get close to that, but they stumbled on the last process generation. So as of today, there is one company in the world, TSMC, that makes all the most advanced chips. And it's obviously a high risk factor in the sense that if there was a major earthquake in Taiwan, the $12 trillion chip industry that relies on the advanced semiconductors would have a problem. Okay, next slide. It's even hard to describe the impact TSMC had. Literally any device that anybody is using, has some of their chips. Of course, they manufacture it. They don't sell the chip. It's sold by NVIDIA or Broadcom or whoever. But the breadth that they reach in the entire economy is truly unbelievable. And again, there's perhaps 1,000 of fabless chip companies that have used the services over all these years. Next slide. So this just shows how important continuous process innovation is. And basically for every generation, there's substantial improvements in density, in power consumption, in speed. And it is the fact that TSMC has been able to deliver each of these generations every other year, which is keeping up Moore's law and the continuous, improvements in the process technology that allows Moore's law to continue, all these years. So again, this is just shows the last couple of years, and the scary part about this slide is that each process generation is in fact more expensive than the last. So the only way to really make this work is in high volume, which of course TSMC has, and being able to deploy, tens of billions of capital every year. So TSMC has committed to spend, hundreds of billions over the next many years to keep this up, and they do have the business model to fund this. So it's a market that's hard to enter. You need a lot of capital to build a new advanced fab. But it is also a market where it's not healthy that there's a single company today that has this, the only one that has this capability. Next slide. This actually shows how tough it is, or how, I don't know the right word here is, how challenging this is, even for TSMC. This is from their Q1 report for this year. And if you show the graph in the lower right, the blue color is their 7 nanometer revenue, right? Which is still going on and predicted. It has been kind of flat actually for the few years before. The red color is the 5 nanometer, which kicked into production at the end of 2020 and then ramped in 21. And as you can see, within 2 years, the new process, the 5 nanometer in this case, was like 30 to 40% of their total output. It was that fast. So if they don't have this next process, they cannot grow. So they have to, and this doesn't predict what they're going to do for 3 nanometer, but we can certainly believe it will look very similar. So both the opportunity to grow and the only way to grow is to keep investing in the next generation of Moore's law. Next slide. So fabless clearly is how the world has evolved, and this is true for the whole world. Right now, the vast majority of the fabs are in Asia, both under the US CHIP Act and the European CHIP Act. There's a great desire and now the money available to fund more fabs in Europe and the US, which I do think is very helpful, because as we all know, semiconductors are a very, very strategic technology, and you cannot ship your car or your washing machine even if one chip is missing. So it does make sense to invest in fab capacity around the world to reduce risk factors. Next slide. Which gets me back to one other element that is going up to the right, but unfortunately in the wrong direction here, which is the design cost and the tape-out cost to make these very advanced chips. I just want to touch on this, but the simple truth is, between the actual mask costs, which for a 3 nanometer chip are in excess of $20 million just to make the masks for the chip, right? And the design costs, which include the design tools that you need to be able to validate the chips, the engineering teams that design the chip and do the verification, the simulation tools, and so on and so on. To do an Intel type CPU, $500 million to make one chip. I know it just sounds crazy. Not all of the chips are so expensive. For example, a networking chip, which has a lot of step and repeat, and it's like much simpler than Intel CPU in terms of validation. The estimated design cost for 3 nanometer chip, $150 million. And even a tiny chip, like a chip that you use in a high-speed optics module, which doesn't have much logic function, but you have to tape it out, will still cost you $30 to $40 million. So the cost of making chips, the design cost and tape-out cost is skyrocketing, which means that the only chips that work are the chips that work in volume. So you have to sell a million or millions of these chips to make up the initial tape-out cost to make it economical, right? So this is true for general purpose CPUs, GPUs, any high volume chip. But for low volume chips, it is arguably much tougher. And it may not be economical. So there's a limiting factor, which is the design cost. But I don't know what would bring that down. It's a hard one. Okay, next slide. So let me then switch back to the cars. So most valuable car company in the world, of course, is Tesla. The stock has been going lower lately, but it's still the most valuable company. And obviously, they have led the transition to electric cars, having demonstrated that you can build successful cars in a very advanced manufacturing processes, and so on. Next slide. And we talked earlier, that they focused on vertical integration. They designed their own chips. They designed their own voltage converters. They invested in their own fast charge networks. More importantly, they own all the key hardware and software design decisions internally, irrespective, where the components come from. And they also upgrade their cars all the time with software updates, and their customers expect as much. It really works, meaning you get a new update and something improves, just like the smartphone. Next slide. Now, of course, they have competition. And in fact, let me focus on one competitor that hasn't even shipped a car yet, which is not Apple, but the company who makes the Apple iPhones, which is called Foxconn. You may not be familiar with Foxconn, which is a very large Taiwanese and largely in China-based contract manufacturer. It is, I believe it's the largest private employer in the world. They have 1.2 million workers making iPhones and all kinds of things. And they now decided they're going to be in the car business. So I'm not making this up. This was announced a few weeks ago. So they launched 3 different models. Next slide. They have in excess of 50% market share in those businesses, and they boldly predicted they will replicate their success with electric cars. The initial goal is 5% market share by 2025, but they don't see any limit to the ability to grow that. Next slide. So they have buses, keep going, and so on. But clearly, to build good electric cars, you need to be vertically integrated, which Foxconn has mastered, and you have to innovate in hardware and software, which they've done together with their suppliers. In this case, it may be Apple, okay? So it's widely believed that Foxconn will build the Apple-style car. Next slide. And okay, we know all about EVs. We have to go a little faster here, I'm being told. Next slide. Next, well, electric cars are coming. Next slide. What we do need is larger driving range. And the most important thing here is the better batteries and power semiconductors and building fast charging networks that allow this to happen. And next slide. And just let me focus on charging stations for 2 minutes. Next slide. The Europeans, unfortunately, have set this crazy goal of 1 charger for every 10 cars, which doesn't make any sense, in my opinion. You would need 1 million chargers for 10 million EV cars in Germany alone. And what makes more sense is to convert petrol stations to what's called fast charging, or the very high power charger cars. So the model that people will charge up the car at home only works if you have a garage. It doesn't work if you have an apartment and you don't have a garage. And the model that you charge it at work doesn't really work either, because there's not enough parking spots. Anyway, next slide. So a fast charger is supposed to fill up your car in, call it 20 minutes or less. The slow chargers, which is the goal of the EU legislation, takes hours and hours and hours to fill up the car to the same capacity. And the problem here is, next slide, without the fast charge networks, you cannot actually do the transition to the electrical cars. And it takes major investments in the electrical grid to solve this, and so on. Next slide. So this is an artist's conception, or maybe it's a real picture of a future Shell electric gas station, and with the fast chargers. We need more of these. Next slide. And in Germany, for example, which I have data for, Germany has 14,000 fueling stations with about 100,000 pumps. that fill up, almost 48 million cars on the roads there, and so on. But it doesn't work for EV chargers to not have this capacity. Next slide. So you cannot make it up with faster chargers. Next slide. We have to go faster here. Sorry, too many slides. Now, if you compare this to China, next slide. China has roughly 1 million EV charger stations, of which over 40% are fast chargers, meaning the ones that charge up your car in 20 minutes. Next slide. Whereas in Germany, it is only 6% fast chargers compared to the 65,000 EV chargers. So this is not a good trend because it takes forever to approve or to submit, permit these fast chargers and to put in the high-powered cables for them. Next slide. So basically Germany has to catch up in the ratio of fast chargers and really focus, not just Germany, all of the EU, Austria, to build a fast charging networks where people, they can take a lunch break or take a coffee and their car is charged up and they can keep going. Next slide. Okay, let's just say there's an economic chicken egg problem here, but it has to be solved. Next slide. And next slide. Sorry, I have too many slides here. Next slides. Next slide. Next slides. So I just want to spend the last 2 minutes to talk about the geopolitics here. So the truth is 80% of all advanced chips today are made in Taiwan and Korea. In other words, literally the entire world depends on 2 companies leading this industry. The US, which used to make half the chips many years ago, down to 12% manufacturing, they still sell roughly 50% of all chips. So the revenue is half in the US roughly, but manufacturing is only 12%. It's mostly Micron and Texas Instruments. This should not have happened. I mean, it's a huge risk factor. And one reason this happened, quite frankly, is the stock market doesn't reward large capital investments that last a couple of years. So basically company figured out they have a higher stock price if they don't make the chips and let somebody else make the chips. On the other hand, TSMC in the end was the biggest winner in the fabless model, which we talked about. Next slide. So what do we need to do here? We do need to change incentives. In other words, it cannot be that we run the world by the stock market. And it is the kind of example, like I always quote Airbus in Europe, where in 1975, when Airbus started, a lot of people, including myself, thought this will never work. You make half the plane in Germany, half the plane in France, half the plane in Netherlands, then you fly around these fuselages and then you assemble a plane. Like, how can this make any sense? Well, Airbus today has more market share than Boeing, the previous competitor. Concerted action can work. In other words, this needs really, EU-wide action. We need more capacity for all kinds of process nodes. It makes sense to invest in those products that have higher margin. So investing in memory chips is probably not the best idea. Memory chips always was more or less a commodity. There's US supply, there's China supply, there's Samsung supply. But in other processes, including the most advanced ones or gallium nitride or you name it, there's much more opportunity to drive value. And it does take years to build this capacity. And it takes effort to train the right engineers. But onshoring fab capacity to both avoid economic risk and to be able to innovate more quickly, I believe is absolutely key for the future of the economy, given how much innovation happens at the chip level. And this also includes the rest of the supply chain, packaging, and making the wafers, you name it, which is almost all of which is located in Asia today. So this was actually my last slide. Thank you for your attention. And do we have time for any questions, or did I run over time? I don't know.
Do you hear me? Hello?
Yes, I can hear you.
It's Jasmine. I really want to say thank you. We have time for a few questions, and I really want to underline that you have shown us a very impressive slide set with a lot of data that is highly relevant for Europe, Germany, Austria. And I will ask one question and hand over to Dejan, who asks some questions from the audience. One thing I'm very interested in. I mean, you left Europe. Herman, for example, left Austria to go to the UK, to Cambridge. And it really seems like when you went to the Silicon Valley, you found an environment where you could draw from full resources. You had so many opportunities. Could you do the same thing in Europe as a young person today, or do you still need to go abroad?
Well, there's a lot of differences today than in the 1970s when I came to the United States to study computer science. The main difference, I would say, is the world is a lot more global today, right? In other words, we have the internet, all the information is online. There's smart people in Europe, there's smart people in the US, there's smart people in China, right? So the competitive environment has fundamentally changed. China was not a competitor in 1970, right? They were doing all the wrong things relative to the economy back then. But today, they're the most aggressive competitor of any country, right? So I think the fundamental issue is, we have to compete with innovation, and innovation can happen anywhere. It's important both in startup companies, which do need venture capital. It's important in mid-sized companies. It's important in the largest companies. I mean, nobody is safe from competitors, right? So if you look at the history even of large companies, even in the US, over the last 50 years, many of them just failed or went nowhere, right? And the truth is the companies that failed are the ones who didn't keep up the innovation. So the ongoing wealth creation and the ability to advance is very much tied to the ability to invest in new technologies, new software, new hardware, new chips, wherever you are. It doesn't matter which the country is, right? Now, again, all the tools, all the access. I mean, you can start a fabless company in Austria and still use TSMC, right? You don't have to build the fab. So the fab issue is a little separate. The cost of designing a company today is largely headcount related. And quite frankly, headcount in Europe is much lower cost than Silicon Valley. So if anything, it's more cost effective to start new companies in Europe than in Silicon. This is true, right? The salaries are higher in Silicon Valley. But you have to, one has to focus on innovation. And again, this is true for startups, mid-sized companies, and large companies. Let me just leave it at that.
Yeah, and that would lead me to the next question that is a little bit connected to it. How attractive is it for you as tech investor to invest in Europe compared to the US?
Well, the venture capital is a whole different problem in the sense that, there has been a boom cycle the last couple of years, but this year it's obviously slowing down. And unfortunately, or maybe based on history, the vast amount of venture capital still went to the US and in particular to California and particularly to Silicon Valley. So even in the US, 80% of all venture capital is California and New York. There's states in the US that get literally zero venture capital because, it's too far away from the coast. So there's an ecosystem effect where people invest in, proven entrepreneurs and the ability to pull the team together and people who know the processes and so on. There have been a couple of successful startups now in Europe that became unicorns, of course, not as much in the chip industry, but in software and in other service models. So the belief that you can succeed in Europe is improving. But overall, on the world scale, Europe is maybe 10% of venture capital. US is over half, and China and Asia is a large portion. And like Israel has a higher per capita venture capital investment than in any country in Europe. Mm-hmm. Within Europe, the UK has done the best, I would say. But Germany, the German-speaking countries are, after the UK, per capita the highest.
Okay, maybe one more question. If we need more and more chips, what do you think of supply chain risks and how this can be also a factor for startups and scale-ups?
Well, for startups, it's not an issue. I mean, you're happy to get an audience with TSMC and they're willing to make your chips. You still have to pay them for the tape out. But if you have a good idea, they may give you a discount, or they invest even in your company, or they welcome you. Meaning TSMC is a whole organization to, encourage new chip companies and so on. So people are always interested in new good chips, by the way, because a good chip will grow in volume and become important, and maybe the company gets bought one day, but it's incremental new business. And this includes brand new chips like chips in biotechnology or advanced sensors or advanced optics, where the markets today are still, call it nascent or smaller, but they solve problems you just cannot solve any other way. And as a result, it's a very predictable thing that if the chip works, it's a very cost-effective way to build all kinds of very interesting systems that today are not affordable. So, and I'm sorry that this is one point that didn't make enough in my talk here, which is even though the chip may be a small part of the total system cost, what it does do is enable new systems that you just couldn't build before. And as a result, you can enter the market not at the value proposition of the chip level, but of the system level, which can be revolutionary. So there is a magnifying effect of what the chip does in terms of the ultimate product value that is even much, much higher than the chip by itself, right? So again, the opportunities exist everywhere, but it does need startup funding for the startups. And even in mid-sized companies, it is a commitment required to bet on certain chip developments or making the chip happen. You need the right engineers and to pay for the CAD tools at the tape-out cost, but the payoff can and is very large. And there are some examples of successful chip companies in Austria. I'm sorry, I didn't mention them before, but there's a couple of companies in Vorarlberg, and there's a couple, of course, in even Switzerland. I mean, in tiny countries on the worldwide scale that have done remarkably well in what they're doing, given the scale of the country, but one can always do more. Okay, so I will leave it at this. Thank you very much for your attention, and I hope this was helpful.
Thank you. Thank you very much, Andy. We have one more question, but maybe we can pass it over to you.
No, we have one more. What is
it? Just one more. Does it really make sense to copy TSMC, or do we have to concentrate on our fabrication possibilities to key technologies, for example, sub-10 NM tech and fabrication tools?
Yeah, this is a tough one. So Intel said they will invest in Europe to build a factory here to have local geopolitically de-risk fabrication. The issue with advanced processes is just the size of the investment required. One can build legacy processes at much lower cost. In fact, one can actually buy, you call it used equipment, which is fairly inexpensive, and build local capacity here. And there's a whole market, for semiconductor equipment. The latest generation, very expensive. The older generation, a little less expensive. But it's a multi-billion-dollar market just for used tools and so on. But the bottom line is one should focus on what's strategically important. So, for example, in the car industry, if half the future revenue is power transistors, right? I'm sorry, half of the semiconductor content is power related, I would invest in power chips in Europe because you cannot deliver the car if you don't have the power chips, and they're a large part of the manufacturing chain. It doesn't take a lot of money to design a power transistor, by the way. So designing power chips is trivial compared to a microprocessor. But it helps to have a vertically supply chain integration because you want to reduce the margin stack up, right? So a large car company like Volkswagen Group could easily design or hire somebody to make a fab for them to reduce the cost of the power chips, as an example. Now, it takes a few years to get there, but you're going to use the chips in very high volume. So why not get started now, right? And in the power industry in particular, there's silicon carbide, which is currently viewed as the most advanced high voltage technology, and it's very expensive, but it's actually not the future. There's vertical gallium nitride, which has all the better characteristics, and that's what one should invest in now to get it ready for production by 2030 to cut down the cost. So one still has to make the right investment, but it's totally predictable because we know the cars need so many transistors, right? So it's not a risk factor in that sense. Whereas designing the latest microprocessor, unless you're Intel or AMD or NVIDIA or whatever, it's unless you have the volume, you cannot easily compete with the people who have the whole software environment and the ecosystem around their microprocessors. So that's a much, much harder market to enter than power transistors or any other truly innovative things that don't rely on current ecosystems. So one has to really focus on the new technologies that make the most sense to invest in Europe. And some of them are technologies that are not in production today, right? The next big thing. And this includes some of the optical things we talked about, advanced, new kind of high bandwidth gap and high gap transistors and other things that are not yet in volume production, but can really change the world of cars and other functions. So that's where I would, one has to look at the Martian stack-up. Anyway, my time is out. Thank you very much. Talk to you later.
Thank you, Andy, so much. And we'll be happy to share your slides also with our audience. Thank you for preparing so much material. It is super interesting. And thank you for your time.
Yes.
Goodbye.
Yes. Thank you. Bye-bye.